You sent me some stuff about superposition and the Pauli exclusion principle, two pretty fundamental concepts in quantum mechanics.
Right?
And at first glance, they kind of seem to clash, right?
They do. Yeah, it's a puzzle that's kept physicists busy for, well, quite a while. It makes you wonder how something can be in multiple states at the same time, but still have to follow these strict rules.
It's like a cosmic balancing act or something.
Exactly. But that's what we're diving into today. We're going to try to untangle this paradox. So, to get started, maybe we should talk about superposition first.
Okay, yeah. I remember reading about Schrodinger's cat. That thought experiment always messes with my head a bit. Does that tie into superposition?
It's the classic example, yeah. Imagine a cat
Sup,
stuck
dude?
in a box
Right.
with a device that has a 50-50 chance of releasing, say, a deadly poison. Now, until we open the box and actually look inside,
Yeah.
the cat is in this weird state of being both alive and dead simultaneously.
So it's not just that we don't know the cat's state, it's that the cat is actually in both states at the same time.
Exactly. Now, let's take that idea and apply it to something like an electron.
Okay.
Instead of it having a defined position in an atom, it exists as this cloud of probabilities, kind of like a smear across space, until we actually measure its location.
So instead of ordering the nucleus neatly, like planets around the sun,
Right.
electrons are more like fuzzy clouds of potential locations.
Yeah, that's a pretty good way to think about it. And it's this fuzziness, this superposition of states, that brings us to the conflict with the Pauli exclusion principle.
Right, because the exclusion principle sets limits on where electrons can be within an atom.
Exactly.
Like, I think I read somewhere that it's often compared to a traffic cop.
That's a pretty good analogy. The Pauli exclusion principle basically states that no two identical fermions, like electrons, can occupy the same quantum state at the same time.
Oh,
Think of it as a set of unique addresses within the atom. It prevents them from all piling up in the same spot.
so even though an electron can be in multiple places at once, it still has its own designated spot in the atom.
Exactly. Each electron has this unique set of quantum numbers. They determine its energy level, the shape of its orbital, and its spin. It's like an electron's ID card. No two electrons can have the same combination.
This is where I always get tripped up. If electrons are these blurry clouds of possibility, how can we talk about specific spots or addresses within an atom?
It's a good question, and it gets right to the heart of the paradox.
Yeah.
The key here is understanding that the Pauli exclusion principle doesn't actually apply to the electron's exact position itself, but to its quantum state.
Okay, hold on. I need to back up for a second. What exactly do we mean by quantum state when we're talking about electrons?
Well, think of it this way. The quantum state includes all of an electron's properties, like its energy, its angular momentum, and its spin. And what the exclusion principle is really saying is that no two electrons can share the same combination of all these properties.